Welcome, everyone. We are continuing our discussion of science and religion, and our format is going to be slightly different for this recording because last night in our live class, I had computer problems and it did not record. So I'm just going to go through the slides with my commentary, but we will miss all the interesting interaction and back and forth that we had during the live class. So I'm going to go to screen share and pull up the slide. And here we go. So for the last class or two, we've really been discussing the issue of what I would call the fine-tuning of the universe. And the bottom line in this is that there are lots of different variables. Actually, they're not variables, they're constants. There are lots of different constants in the equations of physics that apply in the universe that relate to the various forces present in the universe. So these forces would include the force of gravity, the force of electrical attraction, the strong nuclear force, the weak nuclear force, the rate of expansion of matter at the Big Bang. They all were at some number that we actually experimentally measure. And what we found through physics is that if we change any of those numbers even slightly, we don't get a universe that would support life, what's called here an anthropic universe. And the odds of it hitting it exactly right are 1 part in 10 to the 10th to the 132nd power. And as I mentioned, when we first went through this, that number is so large that it would just writing it down in sort of normal type, 10-point type, would require a significant portion of the universe. By comparison, the number of atoms in the universe is only 10 to the 78th power. So the odds of a universe that's hospitable to life are very small and seems to be fine-tuned. We're going to be continuing this exploration through a number of elements in this session, both on the concept of our place in the universe, namely in the Milky Way and in our solar system, and then we're also going to look at the DNA and the probability of life forming. So one of the things I thought I would illustrate it here as we kind of get into this subject is this should be a pretty familiar picture for those of you who've had any kind of science. Here's our solar system. There's the orbit of the Earth, pretty close in. And one of the things that simple Newtonian physics tells us is if you have an orbital system, the shape of the orbit is an ellipse. An ellipse you can think of as kind of a squashed circle. So here's the orbit of Pluto, here's the orbit of Neptune. So you can actually see, let's focus on the orbit of Neptune, that at one point Neptune is pretty close to the sun, but out here it's pretty far away from the sun. So if you have an orbit that's elliptical, and the ellipse is, the technical term is eccentric, you've got a problem. Namely, there are times when you're very close to the sun and things are a lot hotter than normal. And there are times when you're pretty far away from the sun and things would be much cooler than normal. So one of the issues is going to be, as it turns out, you need a pretty circular orbit to have a stable climate. And sure enough, the Earth's orbit is the most circular of any of the orbits. The other thing that we'll see is there's a zone here of how far away you are from the sun where you can support liquid water through the course of the year. As you can imagine, if you're very, very close to the sun, such as Mercury, all the water boils off. If you're very far away from the sun, such as the outer planets, all the water is frozen, two conditions that don't support life. And speaking of water, this should be sort of a very familiar concept, namely ice cubes float. This should not be a big surprise to anyone. The reason ice cubes float is that when water freezes, it expands. So the density of ice is lower than the density of water, and ice cubes float. Icebergs float, the Titanic hits one, and ponds float. You can go and play ice hockey on ponds because the water is floating. The ice is floating, I should say. This is actually quite unusual. For most materials, when they freeze, they contract, and so they sink. But water is very different. And here is another part of this concept. Another interesting element of the water molecule. And that is, I think most of us are familiar, at least based on the discussion last night. If you dive into a pond or a deep pool, as you go down, the water gets colder. And this makes sense um, because most materials, as they are reduced in temperature, they contract. That's why a mercury thermometer works. The mercury in the thermometer is a liquid, and as it gets colder, it contracts, so it goes down the scale, and you can measure the temperature. And that's true for water also. So in this chart, here's the temperature in degrees centigrade. Here's the density. One is as it gets heavier and heavier and lighter, and I'm sorry, heavier and heavier down, heavier and heavier, higher density up here, lower density down here. So if you take water at 10 degrees centigrade and you start cooling it, it gets more and more dense, so the water is sinking. But there's another very unusual element to the water molecule, and you can see it vividly right here, which is at 4 degrees centigrade, or about 40 degrees Fahrenheit, the density of water reaches a maximum. And then as the water gets colder and colder, it actually gets lighter. As we'll see in a second, that has a pretty significant effect on life and life formation. So here's a chart I just found the other day, which illustrates this point. So we'll take a look at the summer. So here's a pond in the summer. And I hope you can see the numbers here, but if you can, I'll kind of read them off. You see the thermal gradient in the pond. At the very bottom of the pond, it's a deep pond, water is sitting there at 4 degrees centigrade. And as we go up and closer to the surface, water is going to approach the surface air temperature, which here is 22 degrees, kind of in the mid 70s Fahrenheit. So you have this normal gradient. As the air temperature cools, as water evaporates, as the outside air temperature cools, the water drops till at some point in time, it's all at 4 degrees centigrade. And then in the winter, two important things are happening. The first is what I mentioned before, and that is the heaviest water is the 4 degrees centigrade water, about 40 degrees Fahrenheit, and that's going to occupy most of the pond. And even as it gets colder and colder, the water at the very bottom of the pond will stay liquid, and it will stay at 4 degrees. The ice surface of the pond, first, as the ice forms, it floats. It doesn't sink down to the bottom. And then the ice, once it becomes solid in a lake, in northern climes, it actually protects thermally the water in the pond from freezing. So the fishes and just as important, the algae and the plants and everything can live at the bottom of the pond without freezing and dying. And that is critical for life to continue to exist, but it was also critical for life to form in the first place. And then as things warm up, the ice melts, and we're back, and we continue the cycle. So as it says, the lakes and oceans don't freeze because water reaches a maximum density at 4 degrees. So there's a wonderful concept which my friend Robert Piccioni calls the Goldilocks zone, and he calls it the Goldilocks zone in this idea of not too hot, not too cold, just right. So there are lots of elements about our galaxy, the Milky Way, and even our position in the galaxy and our solar system. Everything is just right. Just to go through this, the Milky Way is a good galaxy. There are no massive black holes at the center emitting radiation that would sterilize planets and prevent life from forming. We're also in a placid group of galaxies that have not collided. If galaxies collide, you have all kinds of things happening between stars that throw off a lot of radiation. We're even in a good position in our galaxy. We are in the suburbs of our galaxy. We're far away from the core of the galaxy, where there is a lot of stellar activity, and so we're not affected by colliding stars and the radiation that would result from the collision of stars. But we're close enough to the center to have sufficient carbon and oxygen for life. Um, if you're far away from the galaxy, from the center of the galaxy, and you have small stars, you don't have heavy elements like carbon and oxygen being created, but we're close enough so that we have the benefit of those heavy elements. And our solar system ages just about right. Um, so the orbits of the galactic neighbors are stable, and they have the benefits of heavy elements already created. Even our sun is a wonderful star. First, and very importantly, our sun is not a binary star. Um, many stars, I don't know what the numbers are, but there are many stars where you have two or even three stars orbiting each other, and you might have planets surrounding these multiple stars. But if you have binary stars, you don't have stable planetary orbits and stable seasons. Even the type of our star and its size and luminosity, its brightness, is supportive of life. If the sun's mass were a third higher, it would quickly burn out. And if the mass were a third lower, the zone where water can exist as a liquid would be 4 times smaller. And the luminosity, the brightness of the star, and the stability of the brightness is also very stable. And very supportive of life formation, only a 3% variation over the last 600 million years. If the star went through cycles of being bright and not so bright, it would be hard to sustain life. We even have good planetary neighbors inside our solar system. We have this massive planet Jupiter, and the effect of Jupiter on its neighbors, namely asteroids and comets, protect us from collisions. Although there was a collision 30 to 50 million years ago, which created the moon. So imagine you have this massive quasi-planet, protoplanet colliding with the Earth. The Earth completely melts, and the heavy elements inside the Earth, namely iron, are in the center of the Earth, and the movement of this iron gives rise to a magnetic field, which sustains this day. Anybody that's ever used a handheld compass knows that there's a magnetic field on the Earth, and the Earth's magnetic field is about 100 times larger than any other planet. And as we'll see in a moment, this protects our planet. It protects the atmosphere from our planet from cosmic radiation. We'll see that in detail in a little bit. And then also the moon is far larger as a percentage of the Earth's size than any other planet any other moon in the solar system. As you may know, other planets like Saturn and Jupiter have many, many moons, but they're all tiny compared to the size of the planet. Even Mars has two moons, two satellites, but much smaller, and that stabilizes the rotation of the Earth, also allows for seasons, stable seasons, and tides. So more on the Goldilocks zone, we are close enough to the sun to allow for liquid water. Think about liquid water in the extremes of heat and cold that exist in the universe. Water is a liquid for only a fairly narrow degree of temperature, from 0 degrees centigrade, 32 Fahrenheit, to 100 degrees centigrade, 212 degrees Fahrenheit. We have liquid water. Liquid water is necessary for life. And it's only 1/100,000th of the solar system that where liquid water can exist, and we're lucky enough to be in just the right place. We are also lucky enough to be on a planet that has almost perfectly circular orbit. Um, our distance to the sun varies only by 1.7%. Mercury varies by 50%. I think the average variation of the planets is something like 60%. So the seas don't boil or freeze over. And our planetary gravity is just right. The size of Earth is just right to have a breathable atmosphere. If our planet were much smaller, gravity wouldn't be sufficient to hold the atmosphere um, to the planet. And if our planet were much larger, there would be many other things in our atmosphere that would prevent it from being breathable. So here's a picture of me. I think this is me uh, seeing the Northern Lights in Churchill, Manitoba, a few years ago. And the Northern Lights are a visualization of the Earth's magnetic field. What's going on with the Earth's magnetic field? So this is also a nice picture from space of the Northern Lights. Basically, the Earth has a um, magnetic field, and it just like a bar magnet, it surrounds the Earth and goes into the Earth in the north magnetic pole and the south magnetic pole. What happens is radiation, particles and radiation from the sun are bombarding the Earth, but the Earth's magnetic field protects us. And so again, looking at this picture, what you're seeing here are impact of solar wind, solar particles on atoms in the atmosphere, causing these atoms to fluoresce, just like a fluorescent light bulb lights up, our atmosphere lights up. So this is a visual indication that these rays and particles are deflected to the north and south pole. If we didn't have magnetic field, the atmosphere of Earth would be stripped, and this is what scientists believe happened to Mars. That we are becoming increasingly convinced that Mars had an atmosphere, and Mars had an atmosphere at one point in time, but because it didn't have a powerful magnetic field, that atmosphere was slowly stripped away. And so here's a video, again, beautifully showing the Northern Lights. And these are the things that I always think of as being awesome. Having correct change and checkout at 7-Eleven, the person behind the counter may say it's awesome, but this is awesome. This is a visual representation of the magnetic field protecting us and allowing our atmosphere to survive. So going from sort of planetary things down to more focused living things, biology. The question is, what is life? And of course, we know life is DNA. And one of the most amazing things, if you think about it, is that life and DNA developed almost immediately after the Earth cooled. We know the time from the Earth cooling. We know when early forms of life developed. And so then the question is this an accident? By the way, DNA is an amazing molecule. I think most of us know it's a twisted helix of a variety of 4 different chemicals. And just preparing for this talk last night, I came across some interesting things about DNA. If you stretched out the helix, it would be 5 feet long by 1/10 millionth of an inch wide. It has these base pairs of chemicals, and it has 3.2 billion base pairs, each molecule of DNA. And there are as many atoms in one set of our DNA as there are stars in the average galaxy. And the DNA of the simplest life form can encode a huge array of possibilities, a 1 followed by over 200,000 zeros. So we know that DNA developed almost immediately. And of course, the critical question in our discussion is, was the creation of DNA an accident or guided somehow? If it was an accident, you have a soup, presumably on the Earth or somewhere else, of chemicals swimming, and maybe a lightning bolt hits it or just the right pressure or something happens, and out pops a molecule of DNA. So in thinking about this, we should realize that DNA was first discovered in 1953, and it took 66 years until 2019 to artificially create DNA for a simple bacteria in the lab. So even working with all the right chemicals, working in the laboratory with all the right equipment, it's not so easy to produce a molecule of DNA. So again, my friend Bob Piccioni wrote a book on this subject, Can Life Be Merely an Accident? And he asks the question, what's the probability that this molecule was accidentally created, not just on Earth, but anywhere in the universe? And I love the way he explains the probability. So if I have a deck of cards and I spread it out and I ask you to pick a card from the deck, and I ask you, okay, your goal is to pick the ace of spades on the very first shot, on the very first chance. The probability of that is 1 in 52. There's 52 cards. You got to get the right one. Tough to do, 1 in 52. That's too easy. Do it twice in a row. You might think it would be 1 in 104, but it's actually 1 in 52 on the first one, and then 1 in 52 on the second one. So it's 1 in 52 squared, or 1 in 2,704 of getting it twice in a row. Still too easy. Do it 5 times in a row. Now we're up to 1 in 380 million or more. Very hard to get that 5 times in a row. Again, discarding magic and tricks. So one of the things that Bob presents is going back to the idea of the viable universe and the probability of a viable universe, one capable of supporting life. The odds of that viable universe is not 5 times in a row, but 40 times in a row. But my favorite is this one. The odds of that DNA was created spontaneously is equivalent to pulling that ace 119,000 times in a row. Possible, but highly, highly, highly improbable. And I think this is summed up by evolution. So the question is, was evolution an accident? Was life an accident? Or was it somehow guided by an intelligent force? Here, when I talk about God, I'm talking about an intelligent force in the universe. So I like the idea that evolution was God's tool for creation. And the Bible has a very interesting phrase in it. In Genesis 1:26, God says, pretty good translation. God said, let us make humanity in our image. So people often ask the question, why does God speak in the first person plural, in our image? Lots of possible answers. One is the royal we. Another one is the traditional Jewish answer that God was talking to the heavenly hosts, the angels and seraphim and so on, surrounding God. Christian answer would be very simple, that God was talking to God's triune self, Father, Son, and Holy Spirit. The answer I like, a more modern answer, is God was talking to the rest of creation. This phrase, let us make humanity in our image. And by the way, God only speaks in this first person plural in connection with the first couple of chapters of Genesis and creation. You know, in the book of Exodus, in the Ten Commandments, God speaks in the first person singular, saying, I am the Lord, your God, who took you out of Egypt to be your God. I like the idea that God was talking to the rest of creation. God was talking to the animals. God was talking to the plants. So I think what God was saying is, I'm going to take DNA, I'm going to take creation, and humanity will be elements of both in our image. Elements of animal life, elements of divine existence. So I think this is a proof text for evolution. So the bottom line, the evidence convinced me that there is an intelligent force behind life on Earth and behind creation. So I know you've seen that I have these quotes, and in this format, I have a chance to dwell on each of them. So here's a Nobel Prize winning physicist. Astronomy leads us to a unique event, a universe which was created out of nothing and delicately balanced to provide exactly the conditions required to support life. In the absence of an absurdly improbable accident, the observations of modern science seem to suggest an underlying one might say, supernatural plan. Fred Hoyle, who we saw quoted in the last discussion, another physicist, said life arising through random chemical reaction was as likely as the assemblage of a 747 by a tornado whirling through a junkyard. Copernicus, so vast without any question is the divine handiwork of the Almighty Creator. We have seen this quote from Stephen Hawking in the last session, who said that if the rate of expansion after the Big Bang had been smaller by one part in this number, 100,000 million, the universe would have recollapsed before life had formed. On the other hand, had it been greater by one part in a million, the universe would have expanded too rapidly for stars and planets to form. And Freeman Dyson, a more modern physicist, said, the more I examine the universe and the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming, namely, was tuned to allow life. A few more. Another physicist, at this moment, it seems as though science will never be able to raise the curtain on the mystery of creation. For the scientist who has lived by his faith in the power of reason, the story ends like a bad dream. He has scaled the mountains of ignorance. He is about to conquer the highest peak. As he pulls himself over the final rock, he is greeted by a band of theologians who have been sitting there for centuries. And Maimonides, writing about 1,000 years ago, says, the only path to knowing God is through the study of science, and for that reason the Bible opens with a description of creation. Again, Maimonides is commenting on the fact that the opening chapters of the Bible are the description of creation. As others have noted, Rashi also goes out of his way to note this. If you thought of the Torah simply as a book of laws, it would open with a set of laws about how to do things to be consistent with Judaism. But the first laws of that nature are actually in Exodus 12, where there are laws about how to conduct the Passover Seder. But the Bible opens with this description of creation. So, some final thoughts on God's existence. I believe the evidence is overwhelming. I resist the temptation to call it proof. But the interesting question is, how does belief in God affect our lives? I asked this question last night. I asked for a show of hands. How many of you believe that there is a North Pole, namely an axis of rotation around which the Earth rotates? And everybody agrees that there is a North Pole. Okay, you believe in the North Pole. Now the question is, how does your belief in the North Pole affect your life? And chances are it doesn't affect it very greatly. So the same question should be asked about God and God's existence. There are many people who will say they believe in God, they don't believe in God, but the important question is, how does belief in God affect our lives? And of course, we keep coming back to this question of uncertainty and free will. Belief is not the same as knowledge. If I have a pen and I hold up the pen, I don't believe in this pen's existence. I have knowledge of the pen's existence. I can measure it. I can weigh it. I can write with it. I know that the pen exists. It's not that I believe the pen exists. I don't have uncertainty about that. Even in the world of physics, there are some levels of uncertainty, however. Most people haven't heard of the concept of the Heisenberg uncertainty principle. And I'll just take a moment to explain it. The Heisenberg uncertainty principle, as part of quantum mechanics, says that you can only know the location and direction, namely the velocity, of a particle within some band of uncertainty. Why is that? Well, think about it. Let's say I have a light atom, let's say a helium atom, and I want to measure exactly where this helium atom is. So how would I measure where it is? Well, I might put it under a super microscope. But how does a microscope work? A microscope works by putting light or some other electromagnetic radiation on the thing I'm looking at, and it bounces off of that into the device and ultimately into my eyes. But if the item is small enough, once you impact it with light, or if it's an electron microscope, electrons, that impact is going to move it. So you can't know exactly where that the atom is, or how it's moving. And we actually see this in slit experiments. I don't have the time to go through those experiments, but we know that it's a reality. The other thing is interesting is wave particle duality. So the question then is kind of a simple question in physics, not such a simple answer, but a simple question in physics is light a wave or is light a particle? And the answer is both. For certain experiments, like splitting light in a prism, the only way you can explain that experiment is to understand that light is a wave. Okay, so light's a wave. But for other experiments, such as the photoelectric effect, here's my calculator. At the very top of the calculator is a photocell, so I don't have to have batteries for this calculator. For other experiments, light clearly behaves as a particle. So the answer is, which is it, wave or particle? The answer is both. And that's the way I like to read the Bible. Sometimes I read the Bible as though it is literally written by God, and the shapes of the letters are interesting, and the misspellings are interesting, and the grammatical structure is interesting. And we read it, certainly the traditional way to read the Bible through rabbinic eyes, we're going to talk more about this in the next session, is to read it as though it is infinitely deep and infinitely full of meaning because it's from God. That's one way to read it. Another way to read it is through the eyes of scholars, which posits that there are different authors, and we look for the signs of different authors, the priestly author, and so on, to understand the Bible. So I read it both ways, and also it's important. There's another example I came across as I was looking at this material to prepare for this talk, and that is, we view the world through two eyes. If I only have one good eye, I lose my binocular vision. I lose depth perception. When I view the world through two eyes, I'm looking at the same thing through the same device, but because of the fact that I have two eyes, I can make out depth perception. It literally adds another dimension to my viewing. So I like this idea of looking at science, looking at religion through multiple ways. And I had another thought. Again, I came across this last night in preparing for this discussion, and I love the idea that the sages of the Talmud, although they had powerful religious beliefs, they acknowledged that science might be right and they might be wrong. And I came across an example of this in the Talmud in Pesachim 94b. If you're looking for it on Sefaria, it's 94b, item number 5. It says the Gemara presents a similar dispute. The Jewish sages say during the day the sun travels beneath the firmament and is therefore visible. The firmament is what God created, where the stars and everything sits. And at night, it travels above the firmament. So that's why it's dark. The sages of the nations of the world say that during the day, the sun travels beneath the firmament, and at night, it travels beneath the earth. So, this was a time when we thought the sun revolves around the earth, at least the scientists did, rather than the opposite. But the amazing thing is Rabbi Yehuda HaNasi says the statement of the sages appear to be correct. And Rabbi Yehuda HaNasi is such an important rabbi that in Jewish tradition, he is simply known as rabbi. That's why this word is bolded and the other ones are light. It says Amar Rabbi, Rabbi. So he's the guy that wrote down the Mishnah, probably the most respected rabbi in Talmudic tradition. And he's saying, it appears as though science may be right, even though our religious beliefs might not be. So that concludes our discussion for the moment. What we're going to get into next time is this question, which I teased you with a few sessions ago: does God care? Because if God cares, whether we, here's the the usual thing that I raised. Does God care whether I'm kind or mean, protect children or torture them, observe the Sabbath or not, or have chicken or pork tonight for dinner? Does God care? Does this force that created the universe, which the Greeks thought of as the unmoved mover, if you think of God as the intelligent force that created the universe, as the laws of physics don't care whether I'm kind or mean. I'm kind to children or torture them, care about my diet. Laws of physics are the unmoved mover, distant, disconnected, that the Greeks talked about, or Abraham Joshua Heschel had a wonderful counter to this, calling God the most moved mover. God is powerfully connected to us and cares passionately about us. If that's true, then God would communicate God's caring. If God really cares about us, God would want to connect with us. And of course, that's what we call revelation. And so the question for Jews is, must I take revelation literally, or can I take it seriously, but not literally? So for Jews, the most significant and interesting question is something that we are going to be celebrating shortly on Passover, which is what happened on Mount Sinai. So with that little teaser, I will stop the PowerPoint presentation and conclude this video, and look forward to seeing you next week, either live or on YouTube. So thank you.